Hello students, welcome to EPG Parshala. I am Sumalay Roy from the Department of Physics and Astrophysics of University of Delhi. Here we are going to discuss about the module application of perturbation theory to a few problems from the paper Quantum Mechanics. So students, let us see what we are going to learn in this module. Learn the example of applying non-degenerate perturbation theory to estimate the first order correction to the energy of one-dimensional anharmonic oscillator when the part-of Hamiltonian is proportional to x square. Learn the above example to estimate the correction when the part-of Hamiltonian is h prime equals to ax cube plus bx to the power 4. Most importantly, we will know to estimate the gravitational energy shift in atomic energy hydrogen. We will also learn to estimate the first order correction in energy level of ground state hydrogen-like atoms due to finite size of the nucleus. Here we consider a few examples to illustrate how the time-independent perturbation theory for a non-degenerate case is used to determine the correction in the ground state energy due to the presence of perturbed Hamiltonian in certain examples whose solutions in terms of energy and eigenfunctions are known. Perturbed harmonic oscillator. Example of the perturbed harmonic, or we said anharmonic oscillator. Let us first consider a case of applying a perturbation to a problem which can otherwise be solved exactly. This will enable us to check the results against the exact expressions. So take the case of linear harmonic oscillator for which the unperturbed Hamiltonian is known to be H0 equals to px square by 2m plus half kx square, where k equals to 0 and the perturbation is proportional to x square. Remember, here H0 and px are the operators, quantum mechanical operators. Now the perturbation here is given proportional to x square and it is given by h prime equals to half of k prime into x square, where k prime is greater than 0. We know the unperturbed energy levels for one-dimensional harmonic oscillators are, we designate it as E subscript n superscript 0 equals to h bar omega into n plus half, where n are integers and 0. That means n equals in can take 0, 1, 2, so on and so forth. Now here omega is nothing but equal to k by m to the power half or square root of k by m. The corresponding unperturbed eigenfunctions of linear harmonic oscillator wave functions given in terms of Hermite polynomials. They are psi nx equals to square root of alpha by square root of pi 2 to the power n into n factorial. This whole thing is under square root into exponential minus alpha square x square by 2 into hn alpha x. That means hn as a function of alpha x. Now here alpha is equal to mk by h bar square to the power 1 by 4, That means it is square root of m omega by h bar. Since the full Hamiltonian with force constant capital K equals to K plus K prime, the perturbed eigenfunctions and eigenvalues can be readily obtained by just replacing small k by capital K in the expression of unperturbed eigenfunctions and eigenvalues. Thus, the perturbed energy levels are expressed as E n0 equals to h bar omega into n plus half into 1 plus k prime by k to the power half. Here also n is an integer or 0, which can take different values like 0, 1, 2, 3, 4, so on and so forth. Let us now calculate the perturbed energies up to second order in perturbation theory. According to equations 27.12 in the preceding module, En1 equals to h prime nn equals to half of k prime and expectation value of x square at nn. And from 27.25, the second order correction is En2, which is equal to 1 by 4 into k prime square into sum over k not equal to n modulus x square k n modulus square divided by En0 minus ek0, where x square kn is equal to x square within the operating with the psi n0 and psi k0, denotes the matrix element of x square between the unperturbed linear harmonic oscillator wave functions psi k0x and psi n0x, which is given by x square kn equal to 1 by 2 alpha square into n plus 1 into n plus 2, where k equal to n plus 2, which is equals to, for k equals to n plus 2, and equals to 1 by 2 alpha square into 2n plus 1 for k equals to n. Comparing the results of perturbation theory with exact result, and x square kn, which is equal to 1 by 2 alpha square into n minus 1 for k equal to n minus 2 and equal to 0 otherwise. Thus, En1 equals to half of k prime 1 by 2 alpha square into 2n plus 1 equal to h bar omega into n plus half of k prime by k, and En2 equals to 1 by 4 k prime square multiplied by x square n minus 2 n modulus square divided by 2 h bar omega plus x square n plus 2 n modulus divided by 2 h bar omega, which is equal to h bar omega into n plus half into 1 minus 8 k prime square by k square. Now it is very difficult to check that the results 28.11 and 28.12 can also be obtained from the exact expression 28.6 when we expand the bracket in 28.6 1 plus k by k prime to the power half up to the second order in k prime by k. Note that as long as k prime by k is less than 1, this expansion is going to converge, as the ratio Enj plus 1 by Enj turns out to be independent of n. The condition for convergence is independent of the size of the energy shift. Example 2. Let us now consider the case of an anharmonic oscillator when the Hamiltonian is given by H operator equal to px by 2 px square by 2m plus half a kx square plus ax cube plus bx to the power 4. One encounters such an anharmonic corrections in the study of vibrational spectra of molecules. We shall assume that b greater than 0 to ensure that the energy spectrum would be continuous and unbounded towards negative, as well as positive energies. The perturbation part of the Hamiltonian H prime with lambda equals to 1 is H prime equals to ax cube plus bx to the power 4. So the first order correction to the energy of the nth state is En1 equals to a into x cube nn plus b into x to the power 4 nn, which is again equal to integration minus infinity to plus infinity ax cube plus bx to the power 4 into psi n1 x modular square dx. We have learned in the module on the study of linear harmonic oscillator that the wave functions have definite parity, that is, they are even when n is even and odd for odd n. Since psi n1 x bar x or modular square is always an even function of x, whereas x cube is an odd function of x, the diagonal matrix element x cube nn vanishes. As a result, the perturbation term x cube nn does not contribute to En1. The matrix element of x to the power 4 nn is worked out to be x to the power 4 nn equals to 3 by 4 alpha to the power 4 into 2n square plus 2n plus 1. Now, effect of first order energy shift. Thus, the first order energy shift is designated as E subscript n superscript 1, that is the first order, which is equals to B multiplied by x to the power 4 nm, which is matrix element of nm to the power x to the power 4, and is equal to 3 by 4 into B into h bar by m omega square into 2n square plus 2n plus 1. From 28.17, it is clear that for a fixed value of n, the quantity E1 n increases rapidly as n increases. As a result, the perturbation b into x to the power 4 can have an increasingly important effect. Since the validity of the perturbation method requires that the magnitude of the correction term be small compared to the spacing between the unperturbed levels, determined here by h bar omega. We see from 28.17 that reliable results can be obtained only when the values of the parameters b are small for higher values of n. The second order correction to the energy in the state n is, here it is designated by E subscript n superscript 2, which is nothing but the second order excited state, is equals to sum over k, but here k is not equal to n. Now, this sum is over a into x cube kn plus b into x to the power 4 nn, the modular square of the whole thing, which is divided by the energy difference of the zero state between n and k, that is E n0 minus E k0. To evaluate the matrix elements of x cube kn and x to the power 4 kn, it is convenient to use operator method for linear harmonic oscillator that we have studied in one of the earlier modules. For example, from the roles of annihilation and creation, A operator and A dagger operator, it is easy to see that if A is an operator which contains R factors of A and S factors of A dagger, then phi m A phi n vanishes unless R minus S equals to M minus N. This property facilitates the evaluation of the matrix elements of functions of x and p. For example, to evaluate the expectation value phi n x to the power of phi n for phi n, we can use the fact that x operator equals to h bar by 2m omega to the power half into a plus a dagger, and retaining only those terms in the expansion of a plus a dagger to the power 4, which meets the above criterion. We can calculate each term using the property a dagger phi n minus 1 equal to square root of n phi n, and a phi n is equal to square root of n phi n minus 1. We thus get the result given above in 28.16. Similarly, one can see that the matrix element phi m and x cube phi n is non-zero only for m minus n equals to plus minus 1 or plus minus 3, and phi n minus 1 x cube phi n equals to phi n x cube phi n minus 1 equals to 3 into h bar by 2m omega to the power 3 by 2 into n into square root of n, and phi n minus 3 x cube phi n equals to phi n comma x cube into phi n minus 3 equals to h bar by 2m omega to the power 3 by 2 into n minus 1 into n minus 2 to the power half. Substituting the values of the off-diagonal matrix element using the procedure outlined above, the expression 28.18 can be reduced to En2 equals to minus 15 by 4 into a square by h bar omega into h bar by m omega whole cube into n square plus n plus 11 by 30 minus 1 by 8 b square by h bar omega into h bar by m omega to the power 4 into 34 into n cube plus 51 into n square plus 59 into n plus 21 rapidly as n increases. This implies that reliable results with increasing n. It is clear from 28.23 that the magnitude of second order correction En2 increases can only be obtained for smaller and smaller values of a and b. Gravitational energy shift in atomic hydrogen. Now let us apply perturbation theory for non-degenerate energy levels to study the energy shift in the ground state of hydrogen atom due to the effect of gravitational force. The unperturbed Hamiltonian for the hydrogen atom is H0 equal to p square by 2 mu minus e square by 4 pi epsilon 0 into r, where mu is equal to m into m capital MP by small m plus capital MP, is the reduced mass, m being the mass of the electron and MP is that of the proton. The reduced mass is nearly equal to small m when small m is much less than capital M. The perturbation due to the presence of gravitational interaction is given by h prime is equal to minus g small m into capital MP by r, where g is equal to 6.67 into 10 to the minus 11 Newton meter square per kg square is the gravitational constant. To first order in perturbation theory, the energy shift of the ground one state of atomic hydrogen due to this perturbation is E1s1 equals to matrix element of H prime between psi 1x and psi 1s equals to 1 by pi by a integration of minus gm into mp by r into exponential minus 2r by a mu dr, which is equal to minus g small m into capital MP by a mu, where a mu is equal to 4 pi epsilon 0 h bar square divided by mu e square. Since the unperturbed ground state energy of hydrogen atom is given by E1s0 equals to minus e square by 4 pi epsilon 0 square into 2 a mu. The relative energy shift is E1s1 by E0 equals to 8 pi epsilon 0 g small m into capital MP by e square which is nearly equal to 8.8 into 10 to the power minus 40, which turns out to be rather a small number, indicating there is hardly any need to estimate higher order corrections. First order correction to the energy level of the ground state of hydrogen-like atom due to finite size of the nucleus. Let us use perturbation theory to estimate the first order correction to the ground state energy of hydrogen-like atom due to the finite spatial extension, that is finite size of the nucleus, assuming the nucleus to be spherical having charge Ze, which is uniformly distributed throughout its volume. Suppose that potential energy of the electron due to finite size of radius r of the nucleus is Vr is equal to minus J square by capital R into 3 by 2 minus half into small r square by capital R square when r stays between 0 and capital R, and is equal to minus Z square by small r when r is greater than equal to capital R. Note that to simplify the calculation, we are here working in the system CGS, where 1 by 4 pi epsilon 0 equals to 1. In the figure 28.1 given on the next slide, the potential energy Vr is shown as blue line, whereas the potential energy for a point nucleus is indicated as red line. Using perturbation theory, we take the unperturbed Hamiltonian as that of hydrogen atom with a point nucleus V is equal to minus Z square by R, and the perturbed Hamiltonian H prime equals to Z square by capital R into 3 by 2 minus 1 by 2 into R square by capital R square minus Z square minus of minus Z square by R for R less than 0 or for R within 0 and R capital R, and 0 for R greater than equal to capital R. This slide shows a curve which is plotted for Vr as a function of R. It's shown that at Vr is equal to 0, Vr is finite minus 3 into Z square by 2R. The blue curve shows that the variation of potential energy with finite size of the nucleus. The extrapolated red line corresponds to the Coulomb law with point nucleus. First order correction to ground state energy. The first order correction to the ground state energy is then E11, which is equal to integration of psi 100 r h prime psi 100 r dr. Mind it, here r is a vector in general, and where psi 100 r is nothing but 1 by square root of pi into a cube into exponential minus r by a, where a equals to h bar square by zm square. It may be noted that the integration in 28.31 is to be carried out only within the volume of the sphere of radius a. Since the quantity a in 28.32 is the radius of the first Bohr orbit and r is the radius of the nucleus, which means r is much less than a, and the exponential minus r by a is nearly equal to unity. Thus, for r which is in the order of 10 to the power minus 12 centimeter, z is equal to z max is the order of 100. We have a of the order of 5 into 10 to the power minus 9 cm, and so a by r is of the order of 50. As a result, we have approximately E1, that means the first energy state, equals to 1 upon pi a cube into integration 0 to capital R into z square integration of z square r minus z square by capital R into 3 by 2 minus 1 by 2 into r square small r square by capital R square, which is again multiplied by 4 pi r square dr. This integration evaluated and the result is 2 by 5 into Z square by A into R by A whole square. The fact that the correction E11 is greater than 0 is because the depth of the potential well in which the electron moves is decreased on account of the finite spatial extension of the nucleus. Now the unperturbed ground state energy is E10, which is of the order of minus z square m into e to the power 4 by 2 h bar square, which is again equal to minus z square by 2a. Thus, to first order in perturbation theory, the net effect is E1 equals to E10 plus E11, which means E10 taken common out, it becomes 1 minus 4 by 5 into R by A whole square. Now, since nuclear radius is proportional to z to the power 1 by 3 and the first order Bohr radius goes as 1 by z, the net effect of perturbation increases by z to the power 2 by 3 and which varies from one isotope to another of the same element. For hydrogen atom, it is z equal to 1. The first order correction E11 is about 4 into 10 to the minus 9. It is 10 to the minus 9, which is quite small. Having studied this module, you shall be able to first of all learn the example of applying non-degenerate perturbation theory to estimate the first order correction to the energy of one-dimensional anharmonic oscillator when the perturbed Hamiltonian is proportional to x square. If we learn in the above example to estimate the correction when the perturbed Hamiltonian is h prime equals to ax cube plus bx to the power 4, we know to estimate the gravitational energy shift in the atomic hydrogen. We will learn to estimate the first order correction in the energy level of downstate hydrogen-like atoms due to finite size of the nucleus. Thank you.